Chemical importance of voltage. How does voltage associate with chemistry and free energy? Voltage is work done per charge, and it's viewed from the system, it's negative. So the system, from the system point of view, the voltage is negative. It's spontaneous. Mathematically, voltage, or the EMF, is the work done per charge, or negative work, because it's negative, you're going to get work out of it, over Q, which is the symbol for charge. And Q in chemistry deals with a mole of electrons. So Q is NF, where N is the number of moles, and F is a Faraday, and a Faraday is 96,485 coulombs, which is a unit of charge per mole. If you solve for W, you get negative NF E. And remember, work, maximum amount of work, is equal to delta G. So if you get the amount of work max, that is delta E max. So the maximum voltage you can get out of the system will give you the maximum amount of work possible. So if you want a negative delta G, E has to be positive. So since negative delta G is spontaneous, a positive E is spontaneous, which is what we dealt with before. Now we're going to study the effects of concentration. How does concentration of solutions affect the voltage? E naught means standard conditions, which is 1 molar. 1 atmosphere and a bunch of other stuff, but we're dealing with solutions here. So a 1 molar solution will give you E naught. We don't always have standard conditions. Batteries and such are not 1 molar solutions. So if you increase the concentration of the product, the solutions makes the numerator bigger and slows down the reaction. So remember the right over left, so K, products over reactants, so if you increase the concentration of the products, the numerator is bigger, right over left, and it slows down the reaction. Because if you have more things on top, it is actually probably a cube because it's not at equilibrium. As that gets bigger, you slow down. Well, what happens when you make more products? Well, the reaction's going. So what happens to your battery as you use up more and more reactants and make more products? Your battery dies. So that lowers value. If you can have a rechargeable battery, what you're doing is you're reversing the process, you're making more reactants. So if you increase the reactant, you will increase the voltage. So increasing the products will decrease the voltage, increasing the reactants will increase the voltage. They use this in something called a concentration cell. In a concentration cell, you don't have two different metals. You have the same metal in electrodes. So your electrodes, your anode and your cathode, are the same metal or the same substance. And you have the same solutions. The difference being that you have different concentrations. You have a high concentration on one side and a low concentration on the other side. The electrode in the weakest solution is the anode. What this means is that the anode is being oxidized. If you oxidize, you're producing more ions. So what you're trying to do is make the concentrations equal. So you're striving to make the concentrations of the two sides equal to each other. Since it's the anode, you're producing ions, and that's in the weakest solution. This leads us to something called the Nernst equation. I'm going to derive that. It's not important for you to know how to derive it, but it is important for you to know what it is. We remember from the last chapter that delta G equals delta G naught plus RT natural log of Q, where it's not at equilibrium. But we also know that delta G is NFE, so negative NFE equals negative NFE naught plus RT natural log of Q. If we divide everybody by NF, you get E equals E naught minus RT over NF natural log of Q. And substituting values in for R and F and T at 25 degrees, which is standard conditions, 25 degrees Celsius. Simplifies the equation down a little bit. Minus 0.0591 over N. And then change it to base 10 log for some strange and ungodly reason. And N is the number of moles of electrons changed or canceled out. Number of electrons. It's like we saw multiple electrons in the redox reaction. If you make 6 electrons and get rid of 6 electrons, 6 would be the value of N. So you do have to have a balanced redox reaction on these. So you can find the value of E if you know E naught and the concentrations of the solutions. N varies depends upon what the reaction is. And at equilibrium, E equals 0, Q is now K, and you can calculate the value of K, the equilibrium constant for redox reactions, by doing this if you solve for K. So if you know this, and N, you can solve for the Q, which is now K, because we're at equilibrium. The last stuff is in conversions. If you know the time and or current of a voltage, you can do mass conversions. So you can go back and forth between mass change in electrodes, along with the time and the current that you have, depending upon what you have. If you have the time and the current, T times A, the amps, times 1 mole of electrons over a Faraday, 96,485 coulombs, times 1 mole over the charge. The charge is the charge on the ion. So if the metal is going to 2 plus ions or 3 plus ions, it'll be a 2 or a 3, times the molar mass from the periodic table over 1 mole. Molar mass is in grams. And that will give you the mass of the electrode loss or gain, depending upon the anode, which would lose, and the cathode, which would gain. You can reverse the whole thing. You can be given the mass in grams. 1 mole over the molar mass times the charge over 1 mole times the Faraday. So everything's just reciprocal up above. 96,485 coulombs per 1 mole of electrons times, now this is the variance. If you want to find the time, you put A. If you want to find the amperage, you put the seconds. T is in seconds, by the way. And then that will give you, well, if you plug in the amps, you would find the amount of time. If you plug in the time, you'll find the amps. So whatever you plug in here, you'll find the opposite. That concludes this lesson on concentrations and voltage.